Have you ever wondered how programming languages are structured and processed? Well, the answer lies in the concepts of context-free grammar, or CFG, and pushdown automaton, or PDA. CFG is a formal grammar in which every production rule is of a specific form. This form is V to alpha, where V is a non-terminal symbol, and alpha is a string of terminals and/or non-terminals. It's like a rulebook that outlines the structure of sentences in a language. Context-free grammars play a significant role in describing the syntax of programming languages, natural languages, and a wide array of other formal languages. On the other hand, a pushdown automaton is a type of automaton that extends the capabilities of a finite automaton by adding a stack. Imagine a stack of plates. You can only add or remove plates from the top of the stack, not from the middle or bottom. This stack-like structure allows pushdown automata to recognize context-free languages. A PDA consists of a finite set of states, an input alphabet, a stack alphabet, a transition function, and certain initial and final states. In simple terms, PDAs are the machines that process languages based on the rules defined by CFGs. Now you might be wondering, what's the connection between these two? The link is beautifully summed up by the Chomsky-Schutzenberger theorem. This theorem establishes the equivalence between CFGs and PDAs. It means that for every context-free language described by a CFG, there's a PDA that recognizes the same language, and vice versa. It's a fascinating dance of theory and practice, where the rules and their implementation go hand in hand. So, CFG and PDA are two essential components in understanding the syntax and processing of programming languages. They provide the theoretical and practical frameworks that allow us to structure, recognize, and process languages, making them an integral part of computer science and beyond. Now, let's take a closer look at context-free grammar. At the heart of context-free grammar, or CFG, lies a simple but powerful concept. Every production rule follows the form VA. Here, V represents a non-terminal symbol, and alpha is a string that can be composed of terminals and/or non-terminals. Just as in a game of chess, where the rules dictate the movement of the pieces, in CFG, these production rules govern the formation of strings. So, what exactly do we mean by terminal and non-terminal symbols? Think of terminal symbols as the building blocks. They are the smallest indivisible units, much like atoms in the physical world. Non-terminal symbols, on the other hand, are like molecules that can be broken down into these atomic terminal symbols through the application of production rules. CFGs are not just theoretical constructs, they have practical applications in everyday life. They are the linguists of the computing world, defining the syntax of programming languages. Every time you write a line of code, be it in Python, Java, or any other programming language, you unconsciously follow the rules of a context-free grammar. But the scope of CFGs extends beyond programming languages. They also describe the syntax of natural languages, languages that we humans use to communicate every day. So, every time you construct a sentence in English or any other language, you are, in a sense, following the rules of a context-free grammar. Moreover, CFGs are used in describing the syntax of various formal languages. These formal languages are not necessarily spoken or written, but are precisely defined systems of communication used in fields such as mathematics and logic. In summary, CFGs play a crucial role in defining the syntax of various languages, including programming languages. Their simple yet powerful structure allows us to understand and communicate complex ideas, whether we're coding an app or simply having a conversation. Just as important as CFG, we have the pushdown automaton. A pushdown automaton, or PDA, is a type of computing model that extends the capabilities of a finite automaton by adding a stack. This stack is a crucial component as it allows PDAs to recognize context-free languages. But what exactly is a pushdown automaton and what makes it tick? At its core, a PDA consists of 5 key components. First, it has a finite set of states, each representing a different condition or situation within the computation process. Think of these states as different points on a journey that the PDA takes as it processes input. The second component is the input alphabet. This is the set of symbols that the PDA can accept as input. It's like the vocabulary that the PDA understands and uses to make sense of the information it's given. Next up is the stack alphabet. This is a separate set of symbols that the PDA uses internally within its stack. It's like a private language that the PDA uses to organize and manage its internal processes. The fourth component is the transition function. This is a set of rules that guide the PDA from one state to another. Each rule specifies what the PDA should do given a particular combination of current state, input symbol, and top stack symbol. Finally, there are initial and final states, which mark the beginning and end of the computation process. The PDA starts in the initial state and aims to reach a final state once all input has been processed. By adding a stack, the PDA gains the ability to remember information and use this memory to make decisions later on. This is a significant upgrade from a finite automaton, which lacks this kind of memory. So how does this allow the PDA to recognize context-free languages? Well, the PDA uses its stack to keep track of the structure of the input it's processing. It can push symbols onto the stack when it encounters them, and pop them off when it needs to check them. This ability to manage and manipulate a stack of symbols is what allows the PDA to recognize nested structures, which are common in context-free languages. Therefore, PDAs play a significant role in recognizing and processing context-free languages. You might be wondering, how are CFG and PDA related? Well, the answer lies in the Chomsky-Schutzenberger theorem. It's a key principle in theoretical computer science and automata theory that establishes the equivalence between context-free grammars and pushdown automata. This theorem is a bit like a bridge. On one side you have the CFG, a set of rules for creating sentences in a language. On the other side, you have the PDA, a type of automaton that recognizes context-free languages by using a stack. The Chomsky-Schutzenberger theorem is the bridge that connects these two sides. Let's break it down further. The theorem states that for every context-free language described by a CFG, there exists a PDA that recognizes this language. In other words, if you have a CFG, you can build a PDA that will recognize the same set of sentences. But it's not a one-way street. The theorem also works in reverse. For every PDA, there is a CFG that generates the same language. So if you start with a PDA, you can derive a CFG that produces the same set of sentences. This equivalence is incredibly valuable in the study of formal languages. It allows us to switch back and forth between CFGs and PDAs, depending on what's most convenient for the task at hand. Need to parse a language? Use a CFG. Want to recognize a language? Use a PDA. The Chomsky-Schutzenberger theorem also shows us how CFGs and PDAs are interconnected. They are two sides of the same coin, each providing a different perspective on the same underlying structure, the context-free language. So, the connection between CFG and PDA is established through the Chomsky-Schutzenberger theorem, demonstrating their mutual dependence. This theorem is a powerful tool that helps us understand the intricate relationships between languages, grammars, and automata. It's a testament to the beauty and elegance of theoretical computer science. To wrap things up, let's revisit what we've learned today. We began our journey by introducing two fundamental concepts in computer science: context-free grammar and pushdown automaton. A context-free grammar, or CFG, is a formal system of rules that describe the syntax of programming languages, natural languages, and many other formal systems. In a CFG, every production rule is of a specific form. VA. Here, V is a non-terminal symbol, and alpha is a string composed of terminals and/or non-terminals. On the other hand, a pushdown automaton, or PDA, is an automaton that extends the capabilities of a finite automaton by incorporating a stack. This stack is crucial as it allows the PDA to recognize context-free languages. A PDA consists of several elements: a finite set of states, an input alphabet, a stack alphabet, a transition function, and a set of initial and final states. While both CFG and PDA are independently fascinating, the magic truly happens when we explore their connection, and that connection is beautifully encapsulated in the Chomsky-Schutzenberger theorem. This theorem asserts that for every context-free language defined by a CFG, there exists a PDA that can recognize that same language, and conversely, a CFG can be generated for every language that a PDA can recognize. This equivalence between CFG and PDA is not just a theoretical curiosity. It forms a cornerstone of our understanding of how programming languages are structured and processed. It allows us to convert a CFG to a PDA and vice versa, a process that is frequently used in theoretical computer science and automata theory to study the properties of context-free languages and pushdown automata. Understanding CFG and PDA and their interrelation provides a solid foundation for understanding the structure and processing of programming languages. Until the next time, keep exploring and learning.